So, in the last lecture we discussed about the impulse response function and the transfer function, which actually connects the loading response, the loading process to that of the response. We already said for the process to remain stationary and ergodic stochastic process, the connectivity between the load and the response can be established by a parameter which is time invariant and remains linear. Now, let us try to compare this to get what we call as a response spectrum, because now we have only the mean value of the response, we do not have the response spectrum which is over for the entire frequency. We will try to get the response spectrum. Now, let us compare this with the classical dynamic amplification factor. Is given by this is of course for a steady state response. Which is given by 1 by root of 1 minus beta square square plus 2 zeta beta square, where zeta is the damping ratio and beta is the frequency ratio, which is omega by omega n, where omega n is the natural frequency of the system and omega is the excitation frequency applied upon the system. This already we know is an established relationship, we know this, we have derived this. Now, I want to connect this with the transfer function, because transfer function is subsequently connected to impulse response function with this relationship. Therefore, if I connect this to a transfer function, I can easily find out an understanding between the loading process with that of the response process, if this equation is proved to be acceptable to all of us. Now, h of omega will have two components. One, it should give me a representative value of the amplitude. It should give me the representative value of the phase shift, because we know that all the time the response may not be on the same phase as that of the excitation force. So, we should have two components represented in the transfer function. Okay, these are mandatory, that it should give me indications about the amplitude and the phase shift. If this is agreed, then h omega can be rewritten for our understanding as h omega E minus I phi. There is a very specific reason why we have not taken either the cos or a sine function, but we have taken an exponential function of I phi. I will tell you this after I complete the derivation. There is a very classical advantage of this. Let us call C equation number for the current class as 1. This is already we have derived in the last lecture. So, I will retain it for our understanding, but this is the first equation what we will have for this class. Of course, this equation is classically known to us, so it is not to be numbered. So, now this will have two ideas. One, the amplitude will be given by this. For example, let us say to understand this physically, if the transfer function is of magnitude 0.001 and the forcing function P, let us say, is 100 Newton, then the response will be 0.1 meter. How do you get this? This is the transfer function multiplied by the amplitude at that frequency. Okay, so it is a very interesting linear relationship, okay, directly one to one correspondence. If you know the amplitude, if you know the transfer function value, I will be able to predict the amplitude of the response, but this is only predicting the amplitude, there is no phase. So, phi value is important, okay, we have to capture this. Okay. Now, the response in general can be given by in general, let us say the transfer function amplitude, let us say cos omega t minus phi. Now, this has got all components into it. One is the amplitude of the transfer function with a mod value, so that there is no sign protection in this, but the sign will automatically come into representation of u in terms of phi. Let us see question number 2. Now, that is a general expression, okay, where ut is the steady state response, where ut is the steady state response. On the system. Now, let us compare this with a generic expression, because this is the transfer function, but the generic expression is not like this. The generic expression is, if I am looking only for a particular integral, when I am looking only for a particular integral, that is the steady state solution, generally I express this as some amplitude with that of the forcing frequency with a phase lag. That is a general expression we have derived already in the first module. Okay. Now, this amplitude of the steady state is generally considered to be equal to P0 rho by P0 by K is generally considered as the dynamic amplitude factor D, whereas P0 by K is the static response. So, on the other hand, this can be dynamic amplitude factor into P0 by K. Therefore, up of t will be d P0 by K of cos omega t minus phi, which is 1 by root of 1 minus beta square square plus 2 zeta beta square P0 by K cos omega t minus phi, which is up of t. I call this equation number 3. Now, comparing 2 and 3, that is 1 by root of 1 minus beta square square plus 2 zeta beta square P0 by K cos omega t minus phi is compared with h omega P0 cos omega t minus phi. So, from this we can easily infer that h omega is nothing but 1 by K of this value. Where h omega is called the transfer function, where h omega is called the transfer function. So, very interesting. If I know my dynamic amplification factor for a given system, which actually a plot of frequency ratio versus the ratio of the amplitude to the static response, I will be able to get my transfer function very quickly using this expression if you know my response of the system for the static load. 1 by K is nothing but response of the system for a static load for unit load. Okay. This is why it is called response spectrum. We will come to that point. Now, I am going to derive the response spectrum based on this, but now it is a very interesting connectivity. If I know my DAF for unit load, the static response of the system is what I am connecting to my stochastic response of the given system. Okay, I have connected this now. but still h of omega in this case is giving only the amplitude, there is no phase shift. Okay. So, strictly speaking h of omega should be 1 by k of root of 1 minus beta square square plus 2 zeta beta square of E minus I phi. I call this equation number 4. Now, why E I phi? Why E I phi? We could take sine, we could take cos. Okay. There are two reasons for this. The first reason is d by dt of E I phi could be I d phi by dt of E I phi. What does it mean? It means that the derivative of E I phi will remain with the same fashion or the same style or type. Okay. The second thing is E I phi 1 product E I phi 2 will give me E I phi 1 plus phi 2, which is E I phi 3, which remain again the same type. So, even if you multiply, even if you derive or take a derivative, the type of the result will still remain same. Okay. This will give you many advantages when you do the because you will have to take a derivative, you may have to get a product, especially in autocorrelation function, in covariance function you have to take the product and so on. So, the type of using E I phi will give you the same type back even when you do this operation. So, that is an advantage why we are using E I phi here. Now, we are making this statement as h omega now, which is a transfer function. I am able to protect the amplitude of it and I am able to also protect the phase shift of this. Okay. And it is very easy, provided I have the value of the phase shift between the loading and the response. Okay. I can easily find out this, the response, if I know the loading along with the phase shift or with every frequency, because you know beta is frequency dependent. I will plot it later and show you. Now, I am going to use this further to actually derive the response spectrum. So, from equation 4, h omega is known, therefore, h 0, which I would specifically say as S h f x 0. This f x nothing to do with any nonlinear time invariance. This f x is indicating qualitatively this is a transfer function connecting the load and the response. Okay, that is the meaning. So, if a moment I put 0 here, I will get actually 1 by k, is it not? So, mx is nothing but mf by k. Isn't it very simple and linear? So, if I know the mean value of my forcing function or the process, I will get the mean value of the response, which is equivalent to the static value of this response actually. So, it is time invariant and it is linear, okay, which we wanted in a stationary ergodic process. Okay, that is what we got here. Now, from this how do you deduce the response spectrum? So, to do that we will move forward to find out the autocorrelation of the response. Let us say I want to find autocorrelation of the response. One may ask me a question, why? The moment I have an autocorrelation, I will take a fast Fourier transform of this to find the response spectrum. Okay. So, first let us learn the expression for autocorrelation now of the response. I am able to read it, of the response process. Of the response process. So, I am looking for autocorrelation of the response process, or to be very specific I will equate this later, I will call this autocovariance now, I will equate this later, autocovariance, because we have an expression for covariance already, we will equate it later. So, this expression tells me if load process is a zero mean process, then response is also a zero mean process. That is, it is called HFX 0. okay, the 0 mean process. Now for f of t to be a stationary process, for f of t to remain as a stationary process, f dash of t can be assumed as a new function. If f of t is a stationary process, the new function f dash of t can be assumed as below, provided it is a 0 mean process. So that is f dash of t can be equal to f of t minus mf, because it is a 0 mean process. Then let x dash of t be the realization of the response of f dash of t, because correspondingly there will be a response also when you got f dash of t. Now that can be written as impulse response function h f x s, impulse response function h f x s f dash t minus s ds. This is a standard equation what we already have. This way it is called impulse response function, which is connected to my transfer function by an integral. We already know this. Of course, we have only positive realization, because the negative value of this will have no consequence. Now my f dash, okay, I am talking about capital X here, therefore I should say capital F dash, please correct it here. This is capital X, is a full set, this is also a full set which is original. Okay. Now f dash already f of t minus mf, therefore I can write this expression as 0 to infinity f x s f t minus s ds minus integral h f x s mf ds to infinity. Which is nothing but x of t, and we already know this is mean of response from the last derivation in the last class. We already know this, that is mean of the response mx. Now I call this equation number maybe 5. This also shows a very interesting relationship. If the new process, loading process, is a 0 mean process, you will automatically get the response also to be a 0 mean process actually. Okay, it is matching the same. Now x dash of t being a 0 mean process, autocovariance of two processes f t and f dash of t will be same. Okay, that is a deduced logic from statistics. So now how to write this autocovariance for these two? Let us write down that slightly in a different manner. Let us say my xj of t, which is the realization values of x of t, and the new value of xj plus t plus tau, tau is the interval because I am taking the mean about the ensemble, not the time domain, that is the stochasticity or that is the ergodicity in the given process, which is given by, because we already have this expression, I am expanding it slightly in a different manner using these two algorithms, which is given by h fx s1 fj t minus s1 ds1 integral infinity into h fx s2 fj t minus s2 ds2 integral 0 to infinity this ds2. Which can be rewritten as double integral of 0 to infinity hfx s1 hfx s1 hfx s2 fj t minus s1 fj t minus t plus tau minus s2 ds1 ds2. Now, I am going to bring this as an expected value as similar to this. Okay. First, let us understand how the expected value of this will look like. So, expected value of x of t plus tau will look like limit n tends to infinity 1 by n of xj of t plus tau hence I mean we know, I will write this, we know. Even if you do not know this, now you at least know this is known to us. Okay. We already explained this, actually summation only of an ensemble, there is no time dependence, only the tau is the control, we already explained this in the last lecture. So, we know at least this. Now, this expression will become, because I want to rewrite this back in this form, so that I will use the same algorithm for my forces, which I will say double integral of so now I can, using this relationship, I can extend this as ds1 ds2, which can be then simplified as the covariance function Cf, which is having the variables as tau plus S1 minus S2 ds1 ds2. Now, the autocovariance function will be as same as autocorrelation function if for zero mean process. This is actually statistically verified. Okay, this is a verified statement. I mean, this is a verified statement. So I can then say CV of tau, which is similar to this, from this using a fast Fourier transform I can always find out the response spectrum now. I call this equation number 7. Somewhere down the line it is 6, somewhere here maybe we can call all of them as 6, this is 7, because I will refer this further. Let me check. Now let us connect this to my response spectrum. Let Sx omega be the variance spectrum of the response process x of t. Yes, f omega be the variance spectrum of the load process f of t. Now the variance spectrum of x of t can be defined using the Fourier transform of autocorrelation function of this by the Fourier transform of equation 7. So what does it mean is x omega will be 1 by 2 pi of minus infinity to plus infinity. I am taking the Fourier transform of this, which is Cx tau also Cx, I think, be careful, this is Rx, Cx tau, this is not Cv, Cx tau, Cx tau of, okay, because I have used capital tau here. We are using everywhere capital tau, I suppose, capital tau S1 S2, yeah. So Cx tau e minus omega t d tau. Equation number 8. Now substitute for Cx tau from here. So there are 3 integrals, 1, 2 integrals 0 to infinity for these 2 and 1 from minus infinity to plus infinity for this. Okay, let us write that. So the response spectrum is omega is 1 by 2 pi of 0 to infinity of h fx s1 h fx s2 minus infinity to plus infinity of Cf tau plus s1 minus s2 e minus omega tau d tau ds1 ds2. Now in this let us substitute tau plus s1 minus s2 as theta. So d tau will be d theta. The response spectrum 0 to infinity h fx s1, that is the first one, 0 to infinity h fx s2, the second one, 1 by 2 pi minus to plus c of theta, because that is the autocovariance or correlation of the forcing function, C of theta. Now e to the power of minus I omega theta d theta, that is how this is complete. But I am left with still S1 and S2, because actually the integral is not with E, but it is with the tau. Okay. But to make it complete, because the argument is theta here, I am writing like this. So I have to add some more terms here to make it equal to that of equation 7a. So I will do that here as e to the power of I omega S1 minus S2. Of course d S1 S2 are there. So let me check this equation. S1 S2 1 by 2 pi C of theta I omega theta. Yeah, of course this will be actually, please see, this is change of integral order S2 and S1, because I am integrating S2 and S1. Let me separate this. What I will do now here is integration of 0 to infinity h of x S1 ds1. Okay. In fact, e I omega S1 ds1 integral 0 to infinity h f x S2 e I omega S2. There is a minus sign here, minus ds2, and the one which is left over, okay, this is done. Of course one part is here, this is done, one part is here which is minus sign here. The one which is not done is this. I call this as the variance spectrum of the load, because this is actually the load, which I call this as SF omega. Now one is on the positive, other is for the negative. Okay. We all know already, if this is my impulse response function for the given loading, I can write this as h omega, which is the transfer function, because this integral 0 to infinity, if you look back the equation 1 of today, we have this with us. To be very specific, we should say h f x omega. Okay. The other one could be h f x minus omega of SF omega. There is no x here, this is actually the input spectrum, the load spectrum. Okay. There is no transfer function, these are transfer functions. Okay. One is on a positive band of omega, one is a negative band of omega. Okay. Now I want to show that the value in both the cases will remain almost same if the process is stationary and mean, 0 mean process. Okay. Now if h f x omega is a real function, okay, let us take it as a time, is a real function, E minus Ix star will be E minus Ix. We use a star. So then Sx omega can be written as hfx omega, hx omega star, fx omega. What I call this as hfx omega bond square SF omega. Which is my equation for response spectrum if I know the input load spectrum. And we already know the transfer function is related to the linear static response of a dynamic ambient factor of a given system. So we can easily find out the response of this for every omega. If you try to plot this, let us graphically understand this equation. This is very important part of this lecture, let us try to graphically understand this. It is very important. Let us say I have a row, I have a load, let us say this is my load T f of t. I have a system, maybe single degree, what I get is the response of the system, which will be on the same. Let us see. This is a known fact. Okay. If I have the autocovariance of the force, which plots like this, which is C f tau for a value of tau, then I will get Cx tau, that is the response for the value of tau, if I know the impulse response function, which is h fx tau, which will be a plot like this, and this is also established in the last lecture. Now, these two put together will lead to a graphical understanding which is equivalent to this equation, which will be, if we know the input spectrum, if you know the input spectrum, maybe whatever may be the spectrum, I will get my output spectrum, response spectrum, using a connectivity which is mx, the mean value of the response, can be given by the transfer function, mean value of the force, we already know this. Okay. Now, the variance of the response, both are what we call first order statistics, is now minus infinity plus infinity h fx omega okay s of omega dy. Yeah. Call this equation here. Now, this transfer function has a component of two, one beta, other is zeta. Okay, this is actually nothing but a proportion of or a multiplier of dynamic amplitude factor, which has got these two values. Now, for very low value of zeta, okay, let us express it in very low value of zeta, the response spectrum will become narrow banded. Let us plot this for different values of, let us say this is my plot, which is beta, is omega by omega n, and I am plotting here not the DAF, but I am plotting here the h omega. On the other hand, it is nothing but DAF by k. Okay. So, my first value should be 1 by k and so on. Okay. So, I start from here point 1 by k, then 1 by k, 10 by k, let us say I will take 1 by k here, I will take 10 by k here, and I will take 100 by k here for my plot. Okay. So, we all know it will start from 1, because DAF also starts from 1, and as I go omega equal omega n, that is here, it goes up, and for some value of zeta, otherwise it is unbounded, for some value of zeta it becomes very narrow and comes down. And similarly, as you increase zeta, all will start from here and so on. So, for very low values of zeta, the response spectrum actually becomes narrow banded. Okay. So, people have made some idealization in statistics or stochastic response, called this white noise approximation. What is that white noise approximation? If the variation of hfx omega square is greater or faster than sf omega. What does it mean? The variation of sf omega is actually not very serious, more or less linear, but this is not so. Okay. If it is greater, or contrarily, if sf omega variation is slower, that is, this is the input spectrum, the load spectrum. If the variation in load spectrum is slower compared to that of the transfer function, then the approximation is slightly different. Then we can say the variance sigma x square, because here this variation is much faster, much sensitive compared to this variation. That is what we are saying there, okay? Much sensitive. So, I approximate this as, since the variation is faster, I will call this as a constant out of the integration and say represent this sensitivity, taking it out from the integral, where S0 is called white noise approximation called white noise approximation. So, the variance for white noise approximation becomes sigma square S naught is equal to S naught of this, where the input spectrum is modified to S naught. The input spectrum is modified to S naught. So, in this lecture we have summarized that we are able to connect the transfer function to the classical dynamic amplification factor, which we already know in dynamic response. We have also said that they are time invariant, and for a zero mean process, if we know the mean of the forcing function or the forcing process, I can easily find the mean of the response by simply linearly connecting them. And if I know my DAF, the dynamic amplification factor, I can easily find the equivalent static response of that system for unit load, which will give me my transfer function for the given system. Okay. Further, the variance, which is also one of the important statistical information required for stochastic analysis, can be simplified using a white noise approximation using this relationship, which we call as equation number 9, where S naught is modified spectrum of the input data. So, in the next class we will talk about the return period, then we will talk how this can be used for my fatigue analysis for dynamic systems. So, we will stop there for the course.